What is quantum physics? And why does it so often sound as if the universe is improvising itself into existence? The world we know feels solid, dependable, obedient. If you drop a teacup, it falls. If you flip a coin, it lands. If you close your eyes, the moon does not slip out of the sky. Reality appears steady, almost courteous in its predictability. But at the dawn of the 20th century, scientists began to look closer, much closer. And the deeper they peered into the machinery of nature, the stranger it became. They discovered that light does not behave as it should. Sometimes it flows like a wave, spreading and bending, rippling through space. And sometimes it strikes like a particle, arriving in tiny, discrete packets. Matter itself, those supposedly solid building blocks, refuse to stay neatly in one place. Particles could exist in many possible states at once, hovering in a haze of probabilities until measured. And the act of observation did not merely reveal what was already there. It seemed to play a role in deciding the outcome. This was not a flaw in the instruments, not a trick of faulty data. The results were repeatable, precise, undeniable. And with each experiment, the clean architecture of classical physics, so reliable for centuries, began to fracture. Quantum physics is not just a new chapter in science. It is a new language for reality. In this language, certainty softens into probability. Causes do not always march neatly ahead of effects. The universe, at its deepest level, is not a clockwork mechanism, but something subtler, more luminous, more elusive. In this journey, we will move gently through that world. No heavy equations, no demand to memorize names or dates, just a slow unfolding of ideas, one mystery at a time. From the first cracks in classical thinking to the questions that still keep physicists awake at night. At the turn of the 20th century, physics seemed nearly complete. Newton's laws described motion with elegant precision. Thermodynamics was orderly and self-consistent. Maxwell's equations had woven electricity, magnetism, and light into a single graceful theory. It was a golden age of confidence. Some believed that only minor details remained to be polished, tiny specks of dust in an otherwise immaculate room. One of those specks involved a simple question. What happens when you heat an object? Heat a piece of metal, and it glows. First red, then orange, then white. This glow, called black body radiation, seemed straightforward enough, as classical equations predicted how energy should be emitted at different wavelengths. But when physicists followed those equations to their logical conclusion, they encountered something absurd. As the wavelength grew shorter, into the ultraviolet, the predicted energy soared toward infinity, an object glowing with infinite energy, a mathematical catastrophe. This embarrassment became known as the ultraviolet catastrophe. No adjustment to the classical formulas could rescue them. Reality refused to cooperate. Then, in 1900, Max Planck proposed something radical. Almost reluctantly, what if energy is not emitted continuously? What if it comes in tiny, indivisible packets? Little bundles, like coins that cannot be split. He called them quanta. With a single constant, now known as Planck's constant, he described the size of these energy packets. When he inserted this assumption into the equations, the catastrophe vanished. The math aligned perfectly with experiment. The infinities dissolved. Planck himself did not initially believe that energy was truly quantized. He treated it as a clever mathematical trick. But that quiet adjustment, published without fanfare, had cracked open the door to a new world view. A few years later, another puzzle deepened the mystery. Shine light on a metal surface and electrons are ejected. Classical theory predicted that brighter light, stronger waves, should knock electrons free with greater energy. But experiments told a different story. No matter how intense the light, if its frequency was too low, nothing happened. Yet above a certain frequency, even faint light could liberate electrons instantly. In 1905, Albert Einstein proposed a daring explanation. Light, he suggested, is not just a wave. It also behaves as a stream of particles, later called photons. Each photon carries energy determined by its frequency. If a single photon has enough energy, it can eject an electron. If it does not, no amount of additional photons will help. It was as if the universe required the right key, not just more force. Einstein's idea worked. It explained the sharp threshold perfectly. For this, he would later receive the Nobel Prize. Yet even he felt uneasy about the deeper implications that would follow. Because if light could be both wave and particle, what else might refuse our tidy categories? The most unsettling answer emerged from an experiment so simple it borders on childish. Place a barrier with two narrow slits between a light source and a screen. When light passes through both slits, it produces an interference pattern alternating bright and dark bands, just like waves overlapping on water. That made sense. But then physicists dimmed the light until photons traveled one at a time. Surely single photons would behave like particles, passing through one slit or the other, forming two simple clusters on the screen. They did not. Even sent one by one, the photons gradually built up the same interference pattern, as if each photon had somehow passed through both slits at once, as if it explored every possible path before choosing where to land. And when scientists tried to observe which slit the photon actually used, the interference pattern vanished. The photon behaved like an ordinary particle again. The mere act of measuring changed the outcome. It was not that reality disappeared when unobserved. It was that, at its smallest scales, reality does not settle into a single, definite story until interaction forces it to. What began as a minor discrepancy in glowing metal had evolved into something far more profound. The universe, it seemed, was not built from solid certainties, but from possibilities, overlapping, shimmering, waiting. And only when pressed by measurement does one possibility crystallize into fact. The deeper we look, the less the universe resembles a rigid machine. Instead, it feels like a tapestry woven from probabilities, a structure where even emptiness hums with hidden activity. Quantum physics does not destroy reality. It reveals that reality is stranger, subtler, and more creative than we ever imagined. The moment the detectors were switched on, the moment the photons were watched, their behavior changed. They no longer spread out like waves. They no longer painted that delicate interference pattern, the signature of overlapping possibilities. Instead, each photon arrived like an ordinary particle, landing cleanly behind one slit or the other, left or right, this path or that one. No shimmering in between. And then came the detail that made the experiment feel less like physics and more like a riddle. Turn the detectors off and the interference returns. Turn them on and it disappears again. Not sometimes, not approximately, reliably. Like a light switch, like a verdict. At first glance, you might suspect the obvious. The measuring devices must be disturbing the photons, bumping them off course, ruining the wave pattern. But in many versions of the experiment, the setup can be made remarkably gentle. The crucial point isn't brute force, it's information. If the experiment contains a way, even in principle, to know which slit the photon took, then the wave-like pattern collapses. If that which path knowledge is erased, the wave pattern returns. It begins to feel as though reality is sensitive, not to our eyes, but to whether the universe has left behind a record. As though the mere possibility of knowing the path is enough to change what happens. And this is why the double-slit experiment sits at the heart of quantum physics. Because it refuses to fit into the categories we grew up trusting. In the classical world, objects have trajectories. They go through here, not through there. But at the quantum scale, a particle does not behave like a tiny billiard ball with a hidden, definite route. It behaves more like a spread of potential outcomes, a faint, trembling cloud of could be. Only when a measurement is made, only when an interaction forces a choice, does that cloud sharpen into a single, concrete result. Different interpretations try to make peace with this in different ways. Some picture the photon as a wave that splits, flows through both openings, then recombines until measurement ruins the delicate overlap. Others speak more cautiously and say the wave is really a wave of probability, a forecasting tool for what we're likely to see. And the many worlds view imagines something grander still. No collapse at all, only a branching of reality, where every possibility continues in its own thread. But whichever story you prefer, the stubborn experimental fact remains. Until the system is forced to commit, it does not behave as if it has committed. What began as a simple setup, 2 slits, a source, a screen, became a question about reality itself. Is observation an active ingredient? Does information have physical weight? Is the universe in some quiet way unfinished until it is asked precise question? And this isn't just philosophy. The pattern has been measured again and again, using photons, electrons, even large molecules made of hundreds of atoms. Over and over, the lesson returns. At small scales, nature doesn't move along a single track. It hovers in a spectrum of possibilities, and the world we call definite seems to emerge only when those possibilities are forced to resolve. If the double-slit experiment unsettles us, then the next step is the language that describes it. Because quantum physics, strange as it feels, is not chaos. It has rules. Quiet mathematical rules, reliable enough to power your phone and the chemistry inside your body. Near the center of those rules sits an equation spoken of almost like a soft spell. The Schrödinger equation. No lecture in symbols here. What matters is the idea. In the 1920s, physicists were drowning in a paradox. Particles acting like waves, waves acting like particles, until Erwin Schrödinger offered a new kind of description. His equation doesn't say, here is exactly where the particle is. It gives the wave function psi, a mathematical object that gathers everything you can meaningfully say about a system. Not one crisp answer, but a landscape of likelihoods. How strongly each outcome is weighted, and how that entire landscape changes with time. Classical physics draws clean lines, a trajectory you can sketch. Schrödinger's physics draws clouds, rippling distributions that aren't just ignorance, but part of the deepest description. And when you measure, when you demand a definite fact, this wave of possibilities appears to collapse into a single outcome. One result becomes your reality in that moment. Through that interaction, that's why the double slit looks eerie. The interference pattern is the wave function showing itself in public. Possibility behaving like a physical thing, spreading, overlapping, canceling, reinforcing, until the world is forced to choose. Schrödinger's equation is the rule book for how that possibility evolves, smoothly, predictably, like ripples on a pond, except the pond is made of probability. And it works, astonishingly well. It explains atoms, bonding, conductivity and resistance, semiconductors, and even tunneling, particles slipping through barriers they shouldn't cross. One of its classic triumphs is hydrogen. Before quantum mechanics, no one could fully explain why electrons don't spiral into the nucleus. Schrödinger's equation revealed a different picture. Electrons aren't tiny planets. They form standing wave patterns, stable shapes of probability around the nucleus. These are orbitals, not mere metaphors, but regions where you're most likely to find the electron if you choose to look. And still, beneath the success, the haunting question remains. What is the wave function? Just our knowledge, or something the universe itself possesses, until measurement compresses it into fact? Interpretations argue. The equation doesn't. It simply keeps working, silent, elegant, almost indifferent. But even with that compass, there's a limit to how sharply the fog can be cut. Because as quantum theory teaches us to calculate this shifting map of possibility, it delivers a second message. Less like a formula, more like a boundary. In the quantum world, certainty comes with trade-offs. In 1920s language, that boundary has a name, the uncertainty principle. It says that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. Not because our instruments are clumsy, not because we aren't clever enough, but because reality at this scale does not contain those two exact values simultaneously in the way we expect. A common image is that measuring disturbs the particle. Shine light on an electron, and the photon you use to see it kicks it, altering its motion. That part is true as an intuition, but Heisenberg's point runs deeper than disturbance. Even in a perfect, gentlest imaginable measurement, the trade-off remains. It comes straight out of the mathematics of wave functions themselves. A wave cannot be both perfectly localized and perfectly uniform. If you compress a wave into a tight little packet so you can say, it's right here, you necessarily create a spread of wavelengths inside it. And that spread corresponds to a spread in momentum. If the wave is smooth and single-toned, one clean wavelength, then the momentum is well-defined. But the wave is spread out, and the position comes fuzzy. It's a cosmic exchange rate. Sharpen one, blur the other. In formal terms, the product of the uncertainties is bounded below by a tiny constant related to Planck's constant. In everyday life, that lower bound is so small, it's irrelevant. You can track a baseball with exquisite precision without bumping into quantum limits. But for electrons, atoms, and the hidden machinery beneath matter, the uncertainty is not a rounding error. It's a law. Try to confine a particle too tightly, Pin it down to a smaller and smaller region, and its momentum becomes more wildly uncertain. It resists being nailed to a point. Nature pushes back, not out of stubbornness, but because point-like certainty simply isn't the native language of the quantum world. A gentle way to think of it is this: trying to hold quantum reality with absolute precision is like trying to hold fog in your hands. The tighter you close your fingers, the more it slips away. If you loosen your grip, a trace of it remains. Soft, present, but never fully captured. And that is the strange continuity between everything we've seen so far. The double slit, the wave function, the collapse, the probability cloud, the limits on knowledge. It's all one message, told in different accents. At the deepest level, the universe is not built from certainties. It is built from possibilities, structured, lawful possibilities, moving through the world like quiet waves until interaction forces a single note to sound. In many ways, the uncertainty principle feels like a philosophical warning label quietly affixed to the quantum world. It tells us that knowledge has limits, not because our minds are too small or our instruments too crude, but because reality at its foundations is not built like a clockwork toy. Boss, we are not dealing with tiny billiard balls rolling along invisible tracks. We are dealing with possibilities, probabilities, waves that refuse to be pinned down too tightly without changing their nature. And this structured blur is not merely poetic. It has consequences that are wonderfully concrete. It helps explain why atoms don't collapse. At first glance, an atom looks unstable. Negatively charged electrons should be pulled into the positively charged nucleus. Why don't they simply fall inward and stay there? Quantum mechanics answers with a kind of gentle refusal. An electron cannot be imprisoned into a perfectly defined point. If you tried to confine it to the nucleus, forcing its position to be extremely precise, its momentum uncertainty would swell dramatically. That would imply an enormous, physically costly energy. Nature doesn't allow the atom to pay that price. So electrons hover, not out of preference, but because quantum rules leave no other stable arrangement. Uncertainty, in this sense, is not chaos. It is not randomness spilling out of control. It's a disciplined ambiguity, a graceful fuzziness with boundaries. It gives the universe texture. It allows atoms to be stable, chemistry to happen, and matter to organize itself into anything at all. Without it, reality might be too rigid to produce complexity, too sharp-edged to host life. Science often carries a hunger for certainty. Predict, measure, know. Heisenberg's insight flips that hunger on its back. It shows that certain aspects of nature will always resist full capture. And that resistance is not a failure, it's part of the design. In a strange way, the uncertainty principle invites a kind of peace with not knowing, an acceptance of the softness beneath the surface, a reminder that the deepest truths may not come with crisp borders, but with haze and ripples and unfinished edges. And once you accept that softness, the next idea arrives almost naturally, because quantum reality doesn't just blur what we can know. Sometimes it allows contradictions to coexist. In everyday life, things tend to be one way or the other. A coin is heads or tails. A switch is on or off. The world feels cleanly divided into states that don't overlap. But in the quantum world, that tightest separation can dissolve. A system can exist in a superposition, not secretly choosing one outcome while hiding it from you. but genuinely occupying a combination of possibilities at the same time, until an interaction forces it to resolve. Think of a classical coin toss. Even if you don't know the result midair, the coin is always physically in one definite state. Your ignorance is the only uncertainty. But a quantum coin doesn't merely conceal a pre-written answer before measurement. It can be in a weighted mixture of heads and tails simultaneously, not switching back and forth, but existing in a single physical state that contains both. And then, when you measure, when you ask the system to declare itself, the superposition collapses into one outcome, heads or tails. A definite fact appears. This is the same logic that haunted the double-slit experiment. The particle behaves as though it explores multiple paths at once, until information forces it to choose a single story. Superposition is often described using the wave function psi, a mathematical object that encodes the probability structure of a system. Every possible state, left or right, spin up or spin down, lives inside that wave function as a real component of the description. Before measurement, the system is not a single point on a map. It is the map itself, a spread of potential outcomes with different weights. You can picture it like a foggy landscape of futures. A particle doesn't march down one path. It smears itself across the space of what could happen. And when you interact with it, when you measure, the fog condenses into a single illuminated hilltop, a single chosen result, as if lightning briefly reveals one peak and leaves the rest in shadow. This idea led to one of the most famous thought experiments in physics, Schrödinger's cat. A cat in a sealed box, a radioactive atom, a detector, a vial of poison. If the atom decays, the detector triggers, the poison is released, and the cat dies. If the atom does not decay, the cat lives. Quantum mechanics says that before measurement, the atom can exist in a superposition of decayed and not decayed. And if you extend that logic naively, the cat becomes both alive and dead until the box is opened. Schrödinger didn't propose this to be taken literally as a practical setup. It was a critique, an alarm bell, meant to show how unsettling quantum rules become when stretched into the macroscopic world. But the image endured because it captures the emotional core of the idea. Superposition is not just math. It is a challenge to our instinct that reality must always be one thing at a time. And yet, superposition isn't a loophole or a defect. It's one of the most powerful features of quantum theory. So powerful that much of modern quantum technology depends on it. In a classical computer, the smallest unit of information is a bit, 0 or 1. Everything on your phone, photos, songs, messages, is built from long strings of those two states. A quantum computer uses qubits, and a qubit can exist in a superposition of 0 and 1 at the same time. Not alternating, not pretending, but truly occupying a blended state until measured. With many qubits combined, especially when entangled, quantum systems can represent an enormous space of possibilities at once. This can make certain computations dramatically more efficient than classical methods. Not because the machine is magical, but because it is exploiting the native grammar of quantum reality, structured probability. The same principle underpins quantum cryptography, where measurement disturbs the system in a way that reveals eavesdropping. And it powers quantum sensing, where delicate superpositions can detect extraordinarily small changes in magnetic fields, time, or gravity. These aren't science fiction promises, Their real technology is being built right now. But there's a catch, one that brings us back to the theme of fragility. Superposition is exquisitely sensitive. The smallest interaction with the environment, stray photons, vibrations, heat, even collisions with air molecules can destroy the delicate phase relationships that make superposition meaningful. This loss is called decoherence. It's as if the outside world constantly forces the quantum system to choose, collapsing its graceful ambiguity into ordinary classical behavior. Trying to maintain superposition can feel like balancing a feather on the tip of a needle while someone breathes in the next room. The power is real, but it demands isolation and precision. And that fragility opens a deeper question, one that doesn't go away no matter how good the experiments become. Is superposition a feature of reality itself, or a feature of our description? Some interpretations say the wave function represents knowledge, our best possible prediction before measurement. Others argue the wave function is physically real, and the system truly exists in multiple states until forced to resolve. The mathematics remains the same either way. The debate lives in what the mathematics means. But just as you're settling into that thought, quantum physics offers something even more disorienting than both at once. It offers together at a distance. Imagine two boxes sent to opposite sides of the earth. You open yours and find a left-hand glove. Instantly, you know the other box contains the right-hand glove. That's not mysterious. The gloves were decided all along. Quantum entanglement is not like that. Entangled particles are not like pre-packed gloves. They are more like a pair of objects that don't decide what they are until the moment you look. Yet somehow, when one is measured, the other responds immediately, no matter how far away it is. Not because a signal travels between them, not because they whisper faster than light, but because, in a deep sense, they are described by a single shared quantum state, one wave function, one mathematical object spanning distance. Measure one particle here, and the combined state updates everywhere at once. This is what Einstein famously disliked. He called it spooky action at a distance because it seemed to violate locality. The idea that influences must propagate through space over time. In 1935, Einstein, Podolsky, and Rosen argued that quantum mechanics must be incomplete, that hidden variables must exist to restore a more classical kind of order. Decades later, John Bell found a way to test that hope. Bell's theorem produced inequalities, mathematical limits that any local hidden variable theory must obey. And when experiments were performed, those inequalities were violated again and again with increasing rigor. The universe sided with quantum mechanics. Entanglement is real. Local hidden variables, at least in the straightforward sense Einstein wanted, do not seem to be running the show. And still, one comforting rule remains intact. You cannot use entanglement to send messages faster than light. The outcomes of measurements are fundamentally random. You can't choose what result you'll get, so you can't encode a controllable signal. What you can do is reveal correlations when the results are later compared. Instant connection? Yes. Instant communication? No. It's like two people flipping coins on opposite sides of the galaxy. Each outcome is random, yet the patterns match in a way no classical prearranged script can fully explain. Not because the coins talk, but because they are, in some sense, part of the same event. And perhaps that is the most unsettling possibility of all, that separateness, our intuition that here and there are fundamentally distinct, might be a surface level story, because beneath it, quantum theory keeps hinting at a deeper structure, a world where information, correlation, and possibility are stitched together more tightly than space itself. And this is where interpretations begin to diverge. Copenhagen, many worlds, pilot wave theories, relational views, each offering a different way to tell the same experimental truth. If you want, I can rewrite the next paragraph that follows, different interpretations, into a smooth bridge that sets up Copenhagen versus many worlds versus decoherence in the same calm, sleepy documentary tone. Yeah, some people see entanglement as a story about information, about what we can say we know rather than what the system is. Others see it as evidence of something deeper and profoundly non-local, as if separateness is not fundamental but emergent. And then there is a bolder school of thought. That entanglement is not merely a strange quantum effect happening inside space and time, but a clue about what space and time are made of. A few researchers have suggested that space-time itself, its geometry, its togetherness, might arise from networks of quantum connections, from patterns of entanglement woven between countless tiny degrees of freedom. If that were true, then entanglement wouldn't be something that occurs in space. It would be something that helps hold space together. It's an audacious idea, still being tested and argued over, but it hints at a startling possibility. That entanglement may be less about particles and more about reality's underlying scaffolding. And like so many quantum ideas, it isn't only philosophical. Entanglement has practical teeth. It sits at the core of quantum teleportation. Not the Star Trek kind, not the shipping of objects, but the faithful transfer of a quantum state from one place to another, using shared entanglement and classical communication. It underlies quantum key distribution, where security isn't based on secrecy or computational difficulty, but on a physical fact. If an eavesdropper tries to intercept the key, the delicate correlations are disturbed in a way that can be detected. In quantum computing, entanglement allows many qubits to behave as a single coordinated system. As certain operations cannot be broken down into independent actions on each qubit, the computation becomes genuinely collective. Not simply faster in the everyday sense, but more connected, more richly patterned than classical bits can manage. Einstein may have disliked entanglement, but even he couldn't deny its mathematical inevitability once the evidence began to pile up. And while quantum mechanics and relativity still refuse to merge into one seamless theory, each is astonishingly successful in its own realm. Entanglement leaves us with a different picture of the universe. Not a box of separate objects bouncing off one another, but a web of relationships where distant things can be part of one shared description, one joined state, one story told across space. We don't feel it in daily life. You don't wake up entangled with your neighbor. Your coffee doesn't mirror the fate of someone else's spoon. The classical world is too loud, too warm, too interactive. Coherence shatters almost instantly. But at the smallest scales, this quiet coordination is happening everywhere, all the time. An invisible harmony running underneath the apparent loneliness of space. And perhaps that is the strangest thought of all. that even in a universe of vast distances and silent stars, there are still echoes of togetherness, instantaneous, intangible, and stubbornly real. Of course, if quantum physics has a single unofficial mascot, it isn't an equation or a particle. It's a cat. Schrödinger's cat has become the emblem of quantum weirdness, so famous it's sometimes mistaken for parody. And in a sense, it was born from a kind of mischievous skepticism. It was never meant as a blueprint for an experiment, never meant to be taken literally. It was meant to make a point so uncomfortable you couldn't look away. In the 1930s, quantum theory was already working beautifully. Its equations predicted experiments with unsettling precision. But a deeper question lingered. What did the mathematics mean? Was the wave function a real physical entity, or just a clever bookkeeping device? Do particles truly exist in multiple states until measured, or is that only a way of speaking? Erwin Schrödinger, despite giving the world its most elegant quantum equation, was uneasy with how boldly some interpretations extended superposition, especially into the realm of measurement. So he proposed a thought experiment. Imagine a sealed box. Inside is a cat. Also inside, a radioactive atom, a detector, a vial of poison, and a trigger. If the atom decays, a fundamentally random quantum event, the detector fires, the vial breaks, and the cat dies. If it does not decay, the cat lives. Quantum theory describes the atom, before observation, as a superposition of decayed and not decayed. Follow that logic carefully, and the entire setup, the detector, the poison, even the cat, seems to inherit that superposition, alive and dead, at once. Schrödinger's aim wasn't cruelty, it was clarity. The idea feels absurd when applied to a living creature, so where exactly does the quantum world end and the classical world begin? What counts as a measurement? A conscious observer? A detector? Any interaction that leaves a trace? Different interpretations answer differently. Copenhagen says, don't demand more than the theory gives. Measurement is simply when an outcome becomes definite. Many World says, there is no collapse. Every outcome happens. And opening the box just reveals which branch you're in. Decoherence offers another view. In a warm, noisy world, superpositions quickly entangle with the environment, air, light, vibrations, until the delicate quantum coherence is effectively lost. The cat doesn't stay in a clean superposition because it's already entangled with too much of the universe. Despite their differences, all agree on one core fact. Quantum systems are not tiny classical objects waiting patiently to be discovered in definite states. They evolve through structured possibilities, and that leads to a sharper question. If measurement turns possibility into fact, what exactly is the observer? If we are part of the same physical universe, are we simply another link in the chain of interactions that turns quantum haze into classical clarity? Schrödinger's cat is not only about life and death, it's about knowledge and the strange dance between reality and the act of asking reality to declare itself. And once you accept that certainty is conditional, another surprise follows. In the everyday world, a wall is a wall. A tennis ball without enough energy simply bounces back. But in the quantum world, a particle can meet a barrier it shouldn't be able to cross and still appear on the other side. No breaking through, no hidden crack. Just a different rule, quantum tunneling. To understand tunneling, we return once again to the wave function. In quantum mechanics, A particle like an electron is described not as a hard dot, but as a wave-like spread of possibility. And waves do not end sharply at boundaries. They fade, they leak, they extend into regions where, classically, the particle cannot go. So imagine a particle approaching a barrier, an energy hill higher than the particle's energy. Classical physics says, stop, turn around. The story ends here, but the wave function doesn't abruptly hit zero at the barrier. It decays through it, like a whisper, thinning as it passes through a wall. And if the wall is thin enough, that whisper can still reach the far side. If part of the wave function exists beyond the barrier, then there is a small but real probability that the particle will be found there too. Not magic, mathematics, and the consequences are anything but abstract. Radioactive decay, for example, often depends on tunneling. An alpha particle can be trapped inside a nucleus by a barrier. It doesn't have the classical energy to climb. Yet it still escapes because a small portion of its wave function leaks through. Over time, that small probability accumulates into an event. The particle appears outside. The nucleus changes. The element decays. Tunneling also helps explain why stars shine. In stellar cores, hydrogen nuclei are squeezed close together under immense heat and pressure. But even then, they often lack the classical energy to overcome the electrostatic repulsion between positively charged protons. Classical calculations would suggest fusion should be far rarer than it is, yet the sun burns, because at those extreme conditions, wave functions overlap. There is a tiny chance for a nucleus to tunnel through the repulsion barrier and fuse. Multiply that tiny chance by the unimaginable number of particles in a star, and you get a steady, blazing furnace that lights galaxies. Even here on Earth, we use tunneling. The scanning, tunneling microscope can image surfaces at the level of individual atoms by measuring a tunneling current between an ultra-sharp tip and a material, without the tip ever physically touching the atoms. A picture built from probability leakage. And as our technology shrinks, tunneling becomes both a problem and an opportunity. At nanometer scales, electrons begin slipping through barriers that once behaved like solid walls, creating noise in classical electronics while opening doors for quantum devices that embrace tunneling rather than fighting it. Tunneling teaches a quiet lesson. In quantum physics, many boundaries are not absolute. They are probabilities, suggestions, strong preferences, not hard prohibitions. The tennis ball still bounces off the wall, but the electron can glance at that wall and in the soft language of the quantum world say, I think I'll take the shortcut, and somehow nature allows it. Which brings us to one last haunting idea, one that lives beneath all the others. Because if probability can leak through walls and particles can borrow impossible paths for a moment, then what about emptiness itself? In everyday life, nothing seems simple. An empty room, a blank page, the space under your bed, where lost things disappear. We imagine vacuum, especially the vacuum of space, as perfect quiet, a region with absolutely nothing inside it. But in quantum physics, nothing is never truly nothing. What we call the quantum vacuum is restless. It contains no matter in the usual sense, no light, no sound, but it is not empty. Even when you remove every particle you can and cool a system toward its lowest energy state, the vacuum still hums with activity, subtle fluctuations, rising and falling like invisible waves. And it all begins once again with uncertainty. Because Heisenberg's principle doesn't only constrain position and momentum, it also reaches into energy and time, hinting that even empty space cannot sit perfectly still, not for long. That means that even in a region of space where the energy should be zero, energy can still flicker, briefly, subtly, over very short times. In those tiny windows, the vacuum can borrow energy in the only way quantum physics allows, as fluctuations. And those fluctuations can look like particles, appearing spontaneously, all lingering for the faintest moment and vanishing again as if they were never there at all. We call them virtual particles, not because they are imaginary, but because they cannot be observed the way ordinary particles can. You don't catch them directly. You infer them from the fingerprints they leave behind. Small shifts, tiny forces, slight corrections that show up when experiments become precise enough. At first, that sounds like mathematical trivia, but the vacuum has a way of turning trivia into something you can measure. One of the clearest examples is the Casimir effect, a rare moment where the quantum vacuum stops being an abstract background and becomes something almost tangible. Picture two extremely thin, perfectly conducting metal plates placed in a vacuum, held just a few nanometers apart. Classical physics expects nothing dramatic, no air between them, no obvious forces, just empty space. But quantum mechanics says that empty space is never truly empty, and that boundaries matter. Between the plates, only certain vacuum fluctuations can fit. The allowable wavelengths are constrained, like notes that can resonate inside a small instrument. Outside the plates, there are far more modes available, more wavelengths, more fluctuations, more subtle pressure from the vacuum's restless sea. So there's a slight imbalance. The vacuum outside pushes a little more than the vacuum inside. And that imbalance creates a measurable force that nudges the plates toward each other. It's tiny, delicate, yet real. In careful laboratory experiments, those plates have been seen to attract exactly as quantum theory predicts, as if the vacuum itself is gently squeezing them, reminding us that even nothing has structure. And the vacuum's energy is not just a laboratory curiosity. In cosmology, there's the idea of vacuum energy density, the possibility that the energy of empty space contributes to the accelerated expansion of the universe, the phenomenon we label dark energy. We don't yet understand that connection in a complete way, but the resemblance is hard to ignore. A vacuum that hums with energy, shaping reality on the larger scales. There is, however, a shadow on this story, one of the biggest mismatches in all of physics. When quantum field theory tries to estimate the vacuum's total energy, the number it produces is absurdly large, wildly larger than what the universe seems to display. The gap is often described as around 120 orders of magnitude, a discrepancy so enormous it's almost comical, except it isn't. It's sometimes called the worst theoretical prediction in physics, not because the math is sloppy, but because it reveals a deep piece of the puzzle we still don't have. And yet, even with that unanswered question, vacuum fluctuations keep showing up in places where we can test them. In quantum electrodynamics, for example, forces between charged particles can be described in terms of exchanges of virtual photons. In the interior of a proton, the mass and behavior we think of as solid are shaped by a turbulent crowd of quarks and gluons, some of them fleeting, virtual, constantly boiling and recombining in a confined quantum storm. Even in atoms, the vacuum subtly shifts energy levels. The famous Lamb shift, a small difference in hydrogen's energy levels, matches experiment only when you include those vacuum corrections. Once you account for the jittery background of empty space, the predictions snap into place with almost eerie accuracy. So in a quiet, almost unsettling way, the vacuum becomes the most fundamental stage of all. Not passive, but active, not blank, but full of potential. Other fields ripple within it. They vibrate on top of it like instruments riding a bass note that never completely stops. Some physicists even suspect the vacuum holds clues to deeper truths still, about quantum gravity, about what space-time truly is, about whether emptiness is the seedbed of structure we don't know yet. But we do know this: the vacuum is not silence. It is a kind of hidden music. And once you accept that even nothingness has a pulse, you begin to notice how often quantum physics overturns the shape of a normal story. Particles don't simply travel in straight lines. They spread into probability clouds. They exist in superpositions. They become entangled. They tunnel through barriers that look absolute from far away. And then, perhaps the strangest turn of all arrives with a question that feels deeply human. What happens when we look? Because in quantum mechanics, measurement does not behave like a neutral act. It feels like a trigger, a sudden change, a pivot point where possibility becomes fact. This is what people call wave function collapse. Before measurement, a particle, an electron, a photon is described by its wave function, a mathematical object that contains all the outcomes that could happen and the weights of their probabilities. The electron is not in one definite place. It occupies a spread of possible places. Its spin isn't simply up or down, it's a combination that includes both. Its path isn't chosen. Many paths are present at once in the theory's description. The wave function is a shimmering fog of maybes. Then you measure. You turn on the detector. You ask a precise question. Where is it? Which way is it spinning? Which slit did it take? And the description changes. The fog condenses into a single answer. One location, one spin direction, one path. Not gradually, not softly, but abruptly, almost like a snap, as though the universe, after holding many options open, decides the instant you demand a result. That alone is unsettling. But the deeper discomfort is this: no one agrees on what causes collapse. Is it a physical interaction with a measuring device? Is it the creation of a record? Information leaking into the world? Is it consciousness? A camera? A stray photon bouncing off the system? The truth is that collapse sits right at the center of quantum mechanics and yet remains strangely slippery. The calculations work beautifully, but the story of what is happening underneath is contested terrain. So different interpretations try to answer the same haunting question in different ways. The Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg, treats the wave function as a tool for predicting probabilities, not necessarily as a physical substance. In this view, or asking what the electron really was doing before measurement isn't meaningful. The electron doesn't carry a definite position waiting to be uncovered. It isn't anywhere specific until measurement makes position a concrete, testable fact. Copenhagen is practical and powerful, but it frustrates people because it seems to dodge the why behind its own rules. That irritation helped fuel the famous coping motto, shut up and calculate, not as a life philosophy, but as a survival strategy inside a theory that keeps working even when its meaning feels unsettled. Other interpretations refuse that shrug. Many worlds, proposed by Hugh Everett in 1957, removes collapse entirely. The wave function never collapses. It evolves smoothly under Schrödinger's equation. Measurement doesn't force one outcome. It entangles you with the system, or in the combined state branches, into correlated worlds. Measure spin, and there is a branch where you see up and a branch where you see down. Both happen. The universe doesn't choose, it splits. Supporters argue this is strange in a clean way. It adds no new rules, only takes the math literally and rejects an extra collapse postulate. The cost is a constantly branching reality that we can't directly visit or compare. Branches decohere, stop interfering, and become effectively separate, raising the testability challenge. Advocates often reply that the goal isn't new predictions, but fewer assumptions. If smooth evolution is already in the equations, why add collapse? Objective collapse theories take the opposite route. Collapse is real physics, sometimes spontaneous, with measurement only increasing the odds. Knowledge-based interpretations instead treat collapse as an update in what an observer knows, clarifying to some, unsatisfying to others, because it shifts focus from the world to our expectations. Then there is decoherence. It doesn't fully solve collapse, but it explains why large, warm, messy systems don't display obvious superpositions. When a quantum system interacts with the environment, air molecules, light, vibrations, it becomes entangled with countless degrees of freedom. Interference doesn't vanish. It disperses into correlations we can't track. So the system looks classical. Decoherence explains why cats don't appear half alive and half dead in practice, but it still leaves the quiet question. Even if interference becomes inaccessible, why do we experience one specific outcome? So, a century in, collapse remains a ghost in the machine, central, useful, and argued over. Quantum physics isn't a single locked room. It's a hallway of doors. Copenhagen, many worlds, collapse theories, decoherence, each offering a different way to speak about the same stubborn facts. Now take one more step down that hallway, and the scenery changes again. What if particles aren't the foundation at all? What if the universe is made of fields, continuous invisible layers spread across space, where particles are localized ripples, brief excitations, notes played on an underlying instrument? Welcome to quantum field theory, where the most basic ingredient of reality is not a thing, but a trembling pattern beneath everything. A familiar example is the electric field, an invisible influence that pushes or pulls charges. Classical fields are smooth and steady. Quantum mechanics refuses that calm. Fields fluctuate, hum, and jitter, even when no real particles are present. The vacuum isn't serene, it's restless. In QFT, everything is a field. Electrons, photons, quarks, neutrinos are not tiny marbles. They are quantized excitations of their corresponding fields. An electron is a localized vibration of the electron field. A photon is a ripple in the electromagnetic field. Color is just the mode of that ripple. If gravitons exist, they would be ripples of a gravitational field. This shift is quietly profound. Particles become convenient labels for certain field behaviors. The field is the deeper reality. It also makes creation and annihilation natural. Add enough energy and fields ring into new excitations, which is why colliders can produce new particles. Antimatter appears as symmetry, different modes of the same field with opposite quantum numbers. Even empty space has structure. Effects like the Casimir force arise because boundaries reshape the allowed field fluctuations. And once you accept the world as fields, a natural next question forms. If the universe is a recipe, what are the ingredients? That leads to the standard model. 6 quarks, 6 leptons, and force-carrying bosons. Photons, W and Z, gluons, and the Higgs. It's incomplete. No gravity, no dark matter, no dark energy, but astonishingly successful. Inside that success lives a crown jewel, QED, the quantum field theory of light and charged matter, so accurate it agrees with experiments to an almost absurd number of decimal places. And that brings us back to the dance, how electrons and photons actually whisper to each other, and why that whisper is precise enough to build the modern world. If you're still awake, you can continue to the next chapter. Otherwise, I hope you sleep deeply and dream gently. Good night.